everyone, and thank you to the organizers for the opportunity. So I'm Sleeba Varghere, and I'm a postdoctoral researcher at Sorbonne University. Today I will be talking about my research on understanding polar solvents through the lens of stochastic density functional theory. So let's talk about polar solvents, from the water in our cells to the solvents that drives the industrial chemistry. Polar solvents are found everywhere, and one of the key defining features of a polar solvent is its polarization dynamics. And this polarization dynamics plays a crucial role in controlling the solvation and reaction rates of chemical reactants and transport and energy storage in systems such in the case of fuel cells and supercapacitors, and protein folding and enzyme activity in the case of biological applications, and specifically in the case of frequency-dependent dielectric permittivity. So successful modeling of a polar solvent demands understanding of its polarization dynamics. So now, how can we explore the polarization dynamics? So of course we have experiments, but today I will be focusing on two other branches, which is the molecular simulation and the theoretical frameworks. In the case of molecular simulation, we have Brownian dynamics, which actually numerically solves the over-down-Langevin equation. In the case of theoretical framework, we use the stochastic density functional theory, which is actually starts from the over-down-Langevin equation and then takes from the particle description to the field description, and under certain linearization approximation, we can obtain analytical expressions for the observable that we are interested in. And so why should we care about it? Because like performing molecular simulations takes time, whereas if you have a reliable theory, you input your parameters and then you get the results for your observable, which can be, if you have a reliably good theory, it saves you time. So what kind of observables that we can look? One is the static structure factor, which is like a snapshot of your system, which gives you information about the dipole, spatial correlation of your dipoles. Then dynamic structure factor, which lets you information about the dynamics of your system or the time evolution of your dipoles. Now, so some of the results that we got is like, the dashed lines are the SGFT predictions, and everything else are the Brownian dynamics results, and we did simulations for systems with varying dipolar strength, so which is indicated by the color bar. So we, from the yellow is for lowest dipolar strength to the blue is for highest dipolar strength. So we also, other thing is that from the standard SGFT, we were able to improve it or extend it by accounting for the short range dipolar correlation by the form in the form of incorporating it with a Cook-G factor. So, and most important thing that we found out was that the SGFT predictions that we obtained are relatively or comparable with the Brownian dynamics results that we get, so which can be seen. In the case, SGFT predictions are the dashed lines in all the cases, and also we have like two components of polarization density, because like the longitudinal polarization density and the transverse polarization density. Longitudinal polarization density is in the top, and the transverse is in the bottom in both cases for the observables, static structure factor and dynamic structure factor. So yeah, coming to the conclusions. So this is the most important thing that we found. Like SGFT can in fact provide the reliable predictions for the system, for the polarization dynamics of the system of a polar solvent. And so it can be as like a perfect fit between experiments and a molecular simulation, where molecular simulation looked at shorter length scales and shorter time scales, whereas SGFT can actually give predictions to the longer time scales and longer collective behavior for the system. And for more info, I welcome you all to come and see my poster. And finally, I would like to acknowledge like my collaborators, Benjamin Rottenberg and Pierre Leon, and also this project was funded by ERC. And for more information about the results that I've spoken about, you can actually see it in this paper. So like this was the first paper about extending stochastic density functional theory to ions in the polar solvent, and this is the results that I obtained during my postdoc. And thank you all for listening. Thank you.